Oh. Now I am recording now. So recording now. So actually, that's fine. So the recording's just going to miss all my blah, blah, blah at the beginning. So anyway, without further ado, let's introduce our first speaker, Blanca Nino. Blanca, take it away.
Okay. Hi, everyone. I'm Blanca. I'm giving a presentation today about the research that I did over the summer, working at CERN remotely. And I was able to work with two mentors from Stanford University, Stanny and Lauren Tompkins, who is her mentor. So my presentation today, I'm going to cover a little bit about the LHC and the new PET group here at Fresno State, and then go into my specific research that involves dark matter. So I'll talk a little bit about that background, the motivation behind the ZH decay, which is my decay and why it's important, and then get to the details of my analysis, which revolves around this idea of fake rates. So about CERN itself, it's the European Organization for Nuclear Research, the world's largest laboratory for high energy research located in Geneva, Switzerland. It's the birthplace of many important discoveries, including several Nobel prizes and the World Wide Web. And the goal of the LHC is to search for new physics beyond what's currently known. What it actually is a 27-kilometer ring of superconducting magnets that work to speed up protons to nearly the speed of light. These protons then collide at four main detectors: ALICE, LHCb, CMS, and ATLAS. And ATLAS is the detector that we work with. So one of the most important discoveries made at the LHC was the Higgs Boson in 2012, which resulted in Peter Higgs and his research partner, Francois Engelbrecht, winning the Nobel Prize in 2013. And this discovery was highly important because it indicates the existence of the Higgs field, which gives particles their mass. Fresno State was the only CSU campus involved in the Higgs discovery, and this was the first research a CSU campus was involved with that resulted in a Nobel Prize. So the NUPET group here stands for Nuclear and Particle Physics Consortium, and it includes 19 schools from the CSU system. Every summer since 2008, we've been able to send 5 to 16 students from the CSU program to Geneva to do research. About 5 students per year are supported by an external National Science Foundation grant. So this past summer, 2020, we were supposed to send 16 students, which is a lot, but it was postponed due to COVID-19. However, 4 students, including 3 from Fresno State, were still able to work remotely with mentors located at CERN. And past students from Fresno State that have worked on ATLAS have gone on to PhD institutions such as Brown, Berkeley, UCLA, UC Santa Cruz, etc. So again, the detector that we are looking at is called ATLAS, and it's one of 2 general purpose detectors at the LHC. And how it works is beams of particles collide at the center of this detector, and these collisions make debris in the form of new particles, which then fly out in all directions. And these particle components fly out through the detector layers, which each record different variables such as transverse momentum, charge, mass, etc. And from this information, we can reconstruct the collision and see particle decay products and their trajectories. So going into a little bit of dark matter background, we'll start with the universe in general. So the universe has been expanding since its birth 15 billion years ago. And it was originally thought that this expansion should be slowing down due to gravity. However, it was discovered that this expansion is actually accelerating. And we're able to see this acceleration through galaxies being pulled apart, as well as supernova redshifts. As a result, scientists attributed this and other phenomena to existence of something beyond visible matter. So things like dark matter or dark energy. And So what we know dark matter is not, is that it doesn't interact with our E and M fields. So we can't see it by charge, it doesn't interact with light. It's not the same thing as antimatter, and it's not like a black hole, like that's regular matter. So possibilities of what dark matter could be involve things like machos, which are massive compact halo objects, WIMP particles, which are weakly interacting massive particles, or something called a dark photon. So building off the standard model and favoring symmetry, the idea proposed is to extend the gauge sector with this new force carrier called a dark photon. It would couple weakly through kinetic mixing with the ordinary photon, and that's how we can detect it. So similar to neutrino oscillations, this dark photon can oscillate between a regular and a dark photon. So my research this summer looks at the production of a Higgs boson in association with a Z boson. And again, through kinetic mixing, that Higgs could then decay into a regular standard model photon and a dark photon. So why this decay? Why is this important? So first, there's a theory that the dark photon could couple to the Higgs. And I'm not 100% sure on the details behind this theory, but this is where we're starting. This is our starting point. So we're looking at the Higgs and assuming that it can couple to our dark photon. So we need to look at Higgs productions. And there's a few different ways that the Higgs can be produced. So we have 4 different channels, but we are specifically choosing ZH because it's a clean decay. So the Z that's produced in association decays into leptons, which are easy to detect. They're easy to trigger in our system. So it gives us a clean signature that we can look at. And then of all of the possible ways the Higgs can be produced, the ZH production channel happens 30% of the time. So we have that constraint that there's a 30% branching ratio of our ZH decay. But apart from that, there are no constraints on what our branching ratio is of the Higgs to dark photon. So we don't know how often that might happen. We don't know yet. That's what we're working on. So okay, so again, we're looking at the Higgs produced with a Z boson, right? So our Higgs decays into a standard model photon, a dark photon, and the Z boson decays into 2 leptons. But if dark matter doesn't interact, how do we detect it? It's detected by missing transverse energy in particle collisions. So the idea is that you would record all other decay products and see if there's energy missing from the system. So the final signature that we're looking for in the detector is 2 leptons, a photon, and this dark matter, which is read as missing transverse energy. However, there's a problem in that this signature can be mimicked by another decay. And this is the decay of a WZ pair into 2 muons, a neutrino, and an electron. And the problem happens when this electron is misidentified as a photon. And this happens fairly often because the electron and the photon have similar tracks in the detectors. So you can see the photon and the electron have a large energy deposit in the hadronic chambers. So they're quite easy to misconstruct. So if this misidentification happens, our WZ decay mimics the final signature of the ZH decay. So this regular photon is mistaken for the incorrectly identified electron, and the neutrino of the WZ decay appears as missing transverse energy, and that's mistaken for the energy of the dark photon. So my project involves determining how often that misidentification occurs and applying that rate of misidentification as a background contribution. So how do we determine this fake rate, this rate of misidentification? It's determined by a formula here, which is just the number of incorrectly constructed electrons over correctly constructed electrons multiplied by identification efficiencies. So these values we took from somebody else's analysis. It's a May 2020 Atlas note. And so we use their values of fake rates based on their electron criteria. So their characteristics of electrons, we used all of that criteria. And so this plot here shows your fake rate as a function of transverse momentum. So it depends on this baseline electron or this leading electron, and that's the one that has the possibility of being misidentified. So your fake rate depends on where you are in the detector. So this absolute eta or pseudo rapidity gives you a higher fake rate the closer you are to the beamline. So as you can see, as the colors get darker, this fake rate number goes up, and that's because the higher eta, you are closer to the beamline and there's less sensitivity closest to the beamline. So you're going to have a higher chance of being misidentified. And your fake rate also depends on the transverse momentum of this baseline electron. So how do we find these fake rates and apply them to our specific decay? So we have a sort of flow chart that explains the steps on how to do this. So first we need to look at the control region on the left. And we call it a probe EWZ control region. So what does that mean? It's called probe E because, again, we're looking at these leading electrons and basing our fake rate values off of that. And it's a WZ control region because we're looking at a region that's enriched in these WZ decays. So we're looking at events that fit the criteria, that fit the signature of this WZ decay. So in this region, we're going to look at each event individually. We're going to assign each event a fake rate based on the properties of that leading electron. Those values are going to be stored and binned. And then we move over to the signal region and we need to scale that data. And that scaling is important because it takes us away from that control region and into the signal region, where the signal region is marked by decays that match the actual decay we're looking at, so the ZH decay. And then once we moved into that signal region, we can apply those values as a background. So a little bit more about these regions and what they mean. So again, the control region is enriched in WZ, WZ potentially misidentified decays. So we're looking at events that have a final signature of 2 leptons and 1 baseline electron, where that baseline electron is where we're getting those fake rate values from. There are 2 jets that correspond to the 2 leptons coming out of that Z boson. And then we have our signal region all the way to the right. And that's where we expect to find that dark photon signal. So the signature of ZH is 2 leptons read as jets and with a single photon. And our missing transverse energy of our signal region is above 60 GeV. So we expect the amount of missing transverse energy to be about half the Higgs. And we're using a standard model Higgs of 125 GeV. So somewhere in between those two lies something called a validation region. And this allows us to apply all of our backgrounds to actual signal data in a region that's removed from where we expect to see that dark photon signal. And we do this in order to make sure that all of our backgrounds are included and match well without biasing the results close to our expected signal. So this validation region is called a blind region. So once we're satisfied with all of our backgrounds and how well they match with the data in the validation region, we can apply the background and data in the signal region, and that's called an unblinding, but it takes a very long time to get there. So right now we're just working in a validation region somewhere that's not where we expect to see our signal. So finally, we have some plots. So what this is we've looked at the control region again. We're looking at events that match our WZ decay. We look at an electron, and based on where it is in the detector, it's sorted by this eta here. And then it's further sorted by its transverse momentum. So this is 2 tables. There are 8 tables overall that give different values, and we bin those values. So we've looked through 1516 data of run 2. We're only looking at 36 femtobarns here, so it's a smaller amount of data. So we can run things quickly to make sure all of our scripts work correctly. And then we'll move on to like larger data sets. But so for this smaller data set, again, we're looking at WZ decays. We found how often this misidentification occurs. And then we sort these events also by transverse momentum. And here's an example of that scaling from the control to the signal region. So on the left, we have the number of events that happen at a particular transverse momentum. So in the control region, again, this is enriched in WZ decays that have a leading electron. We expect to see a lot of events because they have electrons, right? But these events are then scaled down to the signal region, where that region is enriched in ZH decays, which don't feature that leading electron. So we see that about at 50 GeV, there are about 3 misidentifications, which is a very small number, but we don't expect it to be very, very large. We can also see our signal region fake rate values sorted by eta. So again, you see the greater that absolute value of eta, closer to the beamline, you have a higher fake rate, which is the pattern that we expected. And then integrating our signal region plots, we see that there are about 72 events overall that are incorrectly reconstructed. And again, yes, that number is very small. So now that we've sifted through and we found the amount of fake rates, we can actually apply them in action. So we have a validation region of the ZH decay. Again, this is where we expect to see our signal with and without that fake rate added as a background. So our missing transverse energy here is below 60 because we expect our dark photon signal to be somewhere above 60. We don't want to see that yet because we don't want to bias ourselves. So we're going to stay below that. And then we also have a plot of the transverse mass of the pair. So this is the dark photon, or is this the lepton? The transverse mass of the standard model and the dark photon. Again, with and without this fake rate background added. So finally, we have plotted as a function of absolute eta, where we are in the detector, again, following that pattern of the higher absolute value of eta, the higher the fake rate. And you can see that these fake rate values are very small. So this is the log plot on the y-axis, and there's only about 1 event here. But we don't expect, again, for that background to be very big. So in conclusion, we're able to see the application of electron as photon misidentification as a background in specifically the validation region for this small set of run 2 data in our ZH to gamma gamma dark study. But there are still a lot of steps that we have to do in order for this background to be complete. So as mentioned, we're only using a smaller data set. We need to run the whole data set of 139 femtobarns. This whole presentation talked about WZ as a background. There are lots of other decays that can mimic the ZH decay if they're reconstructed incorrectly. So we have to look at all those other potential backgrounds. We haven't included the systematic uncertainties. And apart from electrons being misidentified as photons, jets could also be misidentified as photons. So we have to take that into account as well. So what I've been able to do with this research that I've been working on over the summer is I was able to give a poster talk last semester for the CSM Virtual Research Showcase. Over the summer, I was able to give an international working group talk for the ZH to gamma gamma dark group. I was supposed to give a presentation at the Far West Conference about a month ago, but I couldn't. So a large part of this atlas, like a problem that comes up, is that all of this information is like internal. So things like regional talks or published papers, I'm not allowed to do because I'm not supposed to share preliminary results. But since this is a colloquium, like interdepartmental talk, I can present here. And I'm supposed to be writing my master's thesis on this as well. Hopefully I can submit that before April of next year so that I can graduate in May. And I'm supposed to be going to CERN in January. So thank you to the physics department for your support and standing behind me so I can submit that travel request that was approved by the provost and the department and the president and everything. So right now, the plan is that I'm supposed to go to CERN in January, but that depends on how these COVID things work out. So we'll see. And that's all.
Hey, thanks a lot, Blanca, for an excellent talk. Actually, I forgot to mention, yeah, so Blanca's talk at the virtual symposium last year won first place award, right, Blanca?
Yeah, it did.
Yes. So congratulations. Does anyone have any questions? We'll do a few short questions now, and then at the end, if you guys think of more questions, we'll take like general questions at the end of all the speakers. But any questions now? Okay, I have a question. So the dark photon is supposed to be a dark matter candidate, yeah?
Mm-hmm.
So does it have a mass or it's massless?
It would be massless. So like I said, it would be a counterpart to the standard model photon. So massless, but it would be like a force carrier. Like I said, similar to E&M. Exactly the same, but the only difference is that it's dark.
Dark, okay. So in these decays, then the dark photon would be a massless something. But
yeah.
Okay.
Mm-hmm.
And so well, let me ask you one more follow-up question. So if you're saying photon, so it's a gauge boson, but so the photon is also distinct from other gauge bosons like the W and Z in that it's connected with an abelian symmetry. So a simple, like a linear theory versus a nonlinear theory. So is the dark photon supposed to be kind of like a copy of the regular photon in that it's and then it's linear and abelian, or is it not determined yet?
No, it's linear and abelian. There's, like I said, there's a whole theory explaining why we think that the Higgs can couple. And it, like I said, it's like a mirror of the standard model photon. But that's about the extent that I understand. We didn't get into the theory so much, so we're just doing like the actual applications of searching for decays. Like I said, there's a whole background that I haven't gotten into yet, but I'll probably come to you with questions about that when I'm writing my thesis about it.
Okay, no, that, and I understand that you guys are working on the experimental side and so forth, so that's your primary concern. Okay, well, anyway, thanks again, Blanca. Any more questions? Anyway, think about it. We'll do questions at the end. So up next, so Blanca, go ahead and stop sharing your screen. Our next speaker is Dan Brown, and Dan is also going to tell us about some of his research at on the Atlas project. So Dan, take it away. And unmute, Dan, unmute. Dan,
there it is. Can you hear me now? Okay. Well, I'm Dan Brown, graduate student here at Fresno State. My talk's on this, the title of my talk is "The Search for Higgs Boson Continues Beyond the Standard Model." Hey, so just a little bit about myself. I grew up in Fresno, California, got my bachelor's from Fresno State, ended up getting my teaching credentials through Cal Poly in San Luis Obispo. Taught high school physics and chemistry for a couple of years before returning to Fresno State for their physics master's program. And my research involves a large Atlas collaboration at CERN. Scientists and engineers from all over the world are involved, where there's around 3,000 scientific authors from 180 institutions. And there's around 1,200 doctoral students involved in detector development, data collection, and analysis. And it's one of the largest collaborative efforts attempted in science. Scientists usually work within small groups, choosing the research areas and data that interest them. And any output from the collaboration is shared by all members and is subject to rigorous review and fact-checking processes before results are made public. So so just like Blanca said before, where it's very internal before they put out publications. And like she said, also many discoveries have come out of CERN. Like one of the notable accomplishments was development of the World Wide Web, invented by Tim Berners-Lee in '89 at CERN. Mainly conceived and developed for automated information sharing between scientists around the world. And of course, much more recently, the discovery of the Higgs boson, which contributed to our current standard model. And as of now, it's our best understanding of the universe. And perhaps the graviton will be added next, or even the dark photon, which Blanca's course is currently searching for. And here's just a depiction of protons colliding with like such high energy, other particles spring into existence, causing that cascade of different particles forming and decaying and finally being detected in the detector. So far as a theory, the standard model has been borne out by multiple experiments. So like, why even look beyond the standard model? Well, like Blanca's research going into the dark photon to like dark matter. The masses of matter that don't reflect light and are only detectable through the gravitation interactions. It's unlikely dark matter is already described within the standard model, but in more probable, it just consists of undiscovered particles, such as dark photons. Then there's also baryon asymmetry within our universe, where according to the standard model, the Big Bang should have resulted in equal parts matter and antimatter. And the current model does show some processes that result in a tiny bit more matter being produced than antimatter, but it's far from enough to explain the amount of matter we see today and the lack of antimatter. So since the current model cannot explain these, it must be incomplete. So perhaps we'll be able to fill more gaps in our understanding after the next improvements to the collider are completed. Okay, so this leads us to searching for more Higgs. So as you know, it's newly discovered, which means we still don't know as much as we'd like, and we may never know everything, but we want to know as much as we can. And also, a Higgs is only produced about once in 1 billion collisions, and there's still quite a bit of uncertainty around actually how the Higgs gives particles mass. So there's predictions on Higgs we want to confirm, reaffirm, or even deny, such as like how often the Higgs is produced, just to get more precision on that, how it can be produced, and what it can decay into. So we just need a fuller picture about the Higgs boson. So looking at the theory using Monte Carlo simulations, we can see if data reflects the theory or not. So if not, this could lead to explanations outside our current standard model, and we need to revise. Like perhaps particles don't get their mass the way we think they do. And theoretically, which this will bring me into the research I've been up to, di-Higgs or 2 Higgs bosons can be produced through vector boson fusion. So using Monte Carlo simulations, we want to work on how to identify the Higgs and optimize its production. So my research is working on just optimizing the production of the di-Higgs from vector boson fusion. I've been working with Adam Parker and Catherine Grimm at CSU East Bay. And we work with the vector boson fusion production mechanism as opposed to more common gluon-gluon fusion. So through vector boson fusion, the tau particles produced will decay hadronically to produce additional jets. And what we're doing is we want to cut out as much background as possible while maximizing signal efficiency. So plotting and examining variables to find thresholds to be able to make cuts. And we also worked on the separation of the gluon-gluon fusion from the vector boson fusion, so we can more easily just separate those two production methods. And there's already an analysis working on the gluon-gluon fusion production. And what we also were looking at too was varying the C2v coupling. I'll show this in the Feynman diagram on the next slide. It varies, so varying that varies kind of the probability of the di-Higgs actually being produced. And for most of our purposes, we used Python scripts for like our programming needs. So using Monte Carlo data to analyze different variables, such as momentums, masses, angles, etc., we can compare these to the background events, which are just simulations of other production mechanisms. And we want to cut out events that don't reflect the decay we're looking for. And let's see, if an event reflects the theory of the decay, we may have found an event we're trying to pinpoint, but there's always uncertainty. And then here's the Feynman diagram I mentioned before. Okay, so it represents the vector boson fusion production mechanism, or the main one that we've been looking at. And here's the C2v coupling you can see there, as I mentioned before. So varying that coupling varies kind of the probability of producing those di-Higgs. And the two Higgs are produced from two vector bosons. So you can see those squiggly lines there, fusing, such as like W or Z bosons fusing together to form the two Higgs particles. And we find evidence of those di-Higgs in the final state of two B jets and two tau particles. Okay, and for this mechanism, it's actually a good variable to use would be the Eta angle. So up here, notice the two extra jets, they're symbolized by Q's here. This splits up the forward momentum among more particles being produced. So the angles should be quite a bit steeper here compared to the gluon-gluon fusion mechanism. Okay, so after plotting some of the variables, we get more of an idea where to make cuts. So this literally cuts out events from the data where we're trying to improve the signal significance. Okay, where that significance is just the number of signal events divided by the square root of the number of background events. So comparing the significance before and after we make cuts, we can see if the cuts we made actually improve our significance of the signal or not. And it's challenging for one because of the sheer magnitude of events we're working with. So working with hundreds of thousands of events, which is why we need programming to analyze it all. So again, this shows, say, like the single collision producing particles decaying and finally detected. Our job is to observe those final state particles that are detected and use our software to reconstruct that a Higgs was produced. And remember again that about 1 in 1 billion collisions actually does produce a Higgs particle. And let's see, the most recent steps we've taken have been using the toolkit for multivariate analysis. So it hosts a large variety of multivariate classification algorithms and creates a boosted decision tree to optimize the separation between signal and background. So it goes through pretty much each event, classifying it as either part of the signal or part of the background. And here's two plots produced from the TMVA. So the background rejection versus signal efficiency and the BDT response. So according to the plots, we can get good separation between the signal and background. So in this first one, we can get a signal efficiency around 80% or so while rejecting over 90% of the background. And on the right here, we can see the events identified as background or signal. So the red is background, the blue is signal. So where they're solid blue, that's what the BDT classified as a signal. And where it's red, that's where it classified it as background. And where there's the crossover, it's where it still wasn't quite sure if it was background or signal. So what we can do is, see, make a cut kind of in the middle there and cut everything to the left and see what the new significance would be. But we can't do that yet. So what we're trying to do now is actually weighting these events. Each of the events carries its own weight. So pretty much we need to normalize all the events and then make the cut. Right now we did try and it's way off because it's not normalized. And so far it's actually proving to be pretty difficult because like the TMVA is some complicated programming and it's a little bit of a headache so far. And yeah, so that's where we are right now. So kind of my roadmap and future plans as of now. So since there is the ban on international travel, I was working remotely over the summer. Again, working with Adam Parker and Catherine Grimm. I was able to present to a Slack Atlas group meeting about the research I was doing over the summer. And I was able to present my research at the American Physics Society Far West section this last October, since I was dealing with Monte Carlo and not the actual data. And I plan to work at CERN over the summer of 2021, though fingers crossed, hopefully, and plan to graduate after the summer or fall of 2021, depending on how far I get in my thesis next semester. And if there's anyone here who is interested in high energy particle research, keep in mind you're going to be doing a lot of programming. So like using C++ and perhaps like Python programming. And it's all integrated in with Root, which is kind of the medium that collects all the data. So you'll be programming to usually like search for a specific decay process. So for example, like what I'm doing, searching for the Higgs boson pair production in that BB tau tau final state. So say looking at these two histograms of the mass of the two B jets and the angle between those jets. Okay, so we'd say we want to optimize the signal efficiency. So we do that by making cuts. So for example, the mass of the two B jets, we could make, say, a cut there and there. In this case, the red is our signal and the blue is the background. So cutting to the left of the blue there, or the line, that first line, and to the right of the second line, we'd be able to improve the significance. So cutting out quite a bit of the background while keeping most of the signal. And then say for the angle between those jets, say if we cut around there, everything to the left, it could improve the significance. But it is cutting out quite a bit, or quite a lot of the events. So sometimes we need to be careful when doing this, because cutting out a large amount could improve the significance, but we may have just discarded the event we're looking for. Okay, so, and if you are interested, you can get in contact with Dr. Gao. You'll need to take a couple classes, so particle physics, the physics 163, and tools, skills, work at CERN. So that's dealing with the programming, learning how to use root, and looking and analyzing histograms, and then apply. And so hopefully you'd be able to go here. And then just also just some pictures from past students who were able to go. So here's kind of inside the detector, which you've already seen before. Here's just kind of the overhead view showing just how large it is on the border of France and Switzerland. Very beautiful picture of Geneva right there. So the CERN campus located just west of there. You've already saw this picture too, some students who went to work on research a few summers back. And students enjoying some drinks at a bar in St. Genus on the French side of the border. And sorry, I may butcher some of these French names also. And the ice caves in Chamonix, it's in France near Mont Blanc. And also, last one, the few students hiking the Jura Mountains fairly close to CERN on the French side. And so hopefully I'll be able to go do some of these things next summer too. And that's the last slide.
All right, thanks, Dan. And yeah, we hope as well you'll be able to go to Europe next summer and do some research and hiking and so forth. So are there any questions for Dan? Okay, so actually I have a question. So you were looking at vector boson fusion, so and then getting two Higgs and then looking for the Higgs to decay to a BB bar and then a tau anti-tau, right?
Right, yeah.
Okay, so why not look for like Higgs to decay into like 4 taus, like a two taus and 2 tau bars, or conversely, why not like 2 B's and 2 B bars?
Well, I'm not sure. They may be searching for that. This is what I'm specifically looking for right now.
Okay, so it's a specific type of decay that you're looking for, right?
Yeah.
Okay. All right, so more questions?
What type of Monte Carlo do you use?
Oh, sorry, what was that?
So
What kind of
go ahead.
what kind of Monte Carlo did you use for this model?
Oh, I'm actually not sure. I get all my data from my 2 mentors who have been giving me the different n-tuples and all the data encompassing the signal for this specific decay. But I'll have to ask them about that.
I see. Thank you.
Well, thanks, Dan. And we'll at the end, we'll still, you know, if you guys think of other questions at the end, we'll come back and allow questions to everyone. So Dan, go ahead and stop sharing, and Joey, make sure you're unmuted, and go ahead and share your slides with us. So our last speaker is Joey Contreras. So Joey has been working with me, Dr. Bishop from the math department, and Jae-Young Lee, struggling with quantum gravity. So he's going to tell you what he's figured out about quantum gravity. So Joey, go ahead.
Thank you, Dr. Singleton. Hi, everybody. My name is Joey Contreras, and I'm a grad student at Fresno State. And today I'm going to talk about photon dispersion in quantum gravity using slides that I did from a talk on this very same subject at the last APS Far West section meeting. So in generic models of quantum gravity, there tends to be the prediction of a minimal length. And when I say minimal length, what I mean is like a maximum possible resolution of space-time. And this minimal length tends to imply photon dispersion, which is this idea of photons having energy-dependent velocities. So the at wavelengths comparable to the minimal length, we would expect interaction with the space-time, and so you get these velocities that vary from what they should be, which is the speed of light. One such model was proposed by Emiliano Camella, and in their paper, they talked about this modified energy momentum relation for photons, where we've dropped off the m squared c to the fourth term because photons don't have mass. And there's this correction term which depends on the ratio of the photon energy to the quantum gravity energy scale. By convention, this quantum gravity energy scale is set to be at the Planck scale, so about 10 to the 19 GeV, pretty large. And if you follow through on the math, Taylor expanding out the modified energy momentum relation, you can find that you'll actually see photons with different energies, as shown in this equation right here, where we see the characteristic speed of light c, which is what we expect, but now there is a correction term where we have eta, which depends upon the model that you're using specifically, and again, the ratio of the photon energy to the quantum gravity energy. So testing for this photon dispersion. A prime candidate for this are gamma ray bursts, which are highly energetic photon emissions, typically from events such as neutron stars colliding into one another. They come in two distinctions, short and long, where the line is drawn in terms of burst intervals. And so for an emission less than 2 seconds, we say it's a short gamma ray burst. And for something longer than 2 seconds, we say it's a long gamma ray burst. The short ones are preferable for testing. There is less intrinsic lag associated with them. So for some device, you might get a peak at a detection event, but for long gamma ray bursts, that peak might show up earlier or later than the actual detection was. And so to account for that, short gamma ray bursts appear to be the way to go. And following the expression from earlier about with the photon velocities, we see that different energies would lead to different arrival times. And when I say arrival time, I mean the photon comes from the event and then comes to our detector. And we can see in this expression here that larger length and larger energies will lead to larger differences in this arrival time. And here is a artist rendition of a gamma ray burst. Okay, so GRB 090510. This was a gamma ray burst detected by the Fermi telescope in 2009, where I've also linked the Nature paper to that, if that is something that interests you. And what they did was they searched for Lorentz invariance violation time delay. They used gamma rays in this energy regime. And again, because short gamma ray bursts appear to be the way to go, the burst interval varied between 0.5 seconds to 1.45 seconds. Now, what they did was they found the absolute value of this ratio of delta t versus delta E. And using this, they were able to place constraints on what the quantum gravity energy scale should be. They found that the Planck energy would be 1.6 times, or the quantum gravity energy, I'm sorry, would be 1.6 times as much as the Planck energy. But the expected result would be that the quantum gravity scale should be less than that. For other data, it went as high as 102 times the Planck energy. And so we run into this issue where observational data currently doesn't show the type of dispersion predicted in such generic models. And so we were forced to ask, is space-time smooth? Is there no minimal length scale? And if there is a minimal length scale, it would appear that a new approach is required. And so this is where our research comes into play. where we introduce new forms of the modified momentum operators. And here we choose hyperbolic tangent and inverse tangent. And we choose these because they have bounds. This is loosely motivated by Born-Infeld electrodynamics. But you see, as P gets very large, they have bounds of plus or minus P naught. While at low P, they reduce to the standard momentum operators. Following this through, we see that the modified momentum will actually lead to modified energies in the energy-momentum relationship. For photons in particular, where again we drop this m squared c to the fourth term, the energy expressions become these, equations 8 and 9. And noting here that we have an expression of the form E prime is equal to P prime times C, we see that there is no change to the regular dispersion relationship. All photons should arrive at the exact same time. And so this is convenient because now we have no conflict with observational data of gamma ray bursts. But this was all revolving around this idea of a minimal length scale. And so is there still a minimal length scale in this model? Well, if we keep the standard Heisenberg uncertainty principle, where we have some modified momentum operators, now we modify the position operators such that this relationship is maintained. And here I have the expressions explicitly for the position operators. And I'm going to brush over this, but for more information on it, again, I provided the RVix link, and so I'd be happy to share that at the end. So for the momentum, recall that we chose them because they were in a form that had bounds. And so when the momentum reaches its maximum value, we will see a minimal length value for delta x. And this is also shown graphically right here, where at a high enough delta p, at a high enough delta p, delta x will drop down to this minimum value right here. And so this model maintains a dispersion relationship consistent with the observational data, and it still predicts the existence of a minimal length. And so to wrap it up, modified operators can lead to no dispersion. They need not necessarily lead to that route. This still allows us to have a minimal length. And more importantly, this doesn't conflict with current observational data. And so perhaps we shouldn't be so quick to throw out this idea of a minimal length. And if that's a route that theorists want to go or travel down more in the future, perhaps modified operators are a preferable approach to quantum gravity for proposing such minimal length scales. Thank you.
Thanks, Joey. So are there any questions for Joey? So, okay, I'll ask. So do you, so everything you've done is in context of essentially one-dimensional quantum mechanics. Or are you guys working on generalizations?
Yes, we are working on expanding it out to 3 dimensions, 3 spatial dimensions, and then the time dimension. Still working through the math of it, but yeah, it appears to be working out. We have trivial commutation relations for the position and the momentum, like just with each other. But we do still maintain the general commutation relation when we take x and p together, provided that their dimensions are aligned.
Okay. So any other questions? So any other questions for any of our speakers then? For Blanca, Dan, or Joey? No? Okay. Let me thank our speakers again. Sarah had a little cornucopia.
It's like a party popper.
It's a party popper? Okay.
I think.
Okay, and everyone, let's think good thoughts and keep our fingers crossed for Dan and Blanca to be able to go to CERN. And you know, and Dan, if you need us to talk to actually, so for Blanca, we had to go all the way up to the president. So we asked the dean, and the dean's like, I can't make the decision. So when we asked the provost, he said, I think I can make the decision. Let me check with the president. So it ran all the way up to the president. But anyway, which is a good thing. It's good for the president to know what our students are up to, you know. And so we're keeping our fingers crossed for you guys. And Joey, you're going to be hopefully given another APS Far West section talk next year in Hawaii. So we'll keep our fingers crossed for that. Okay, so anything else? Any final questions? Okay, well, if not, let me thank the students again, and have a great weekend.
Great job.